Dear students, today we are going to discuss Module 5, Industrial Drives and Application. The title of the module is Synchronous Motor Drives. Under this title, today we are going to discuss Sinusoidal Permanent Magnet AC Motor Drives. Okay. So here already we have discussed the basics of permanent magnet AC motor. If the induced voltage in the stator phase are sinusoidal in nature, then we can call it as sinusoidal permanent magnet AC motor. Okay, and here coming to this sinusoidal PMAC motor, that is the three-phase of stator. If the three-phase supplies are supplied to the stator windings with variable frequency with the phase difference of 120 degree. Okay, so that is nothing but all are in sinusoidal in nature. So let us see how the motor behaves when variable frequency current or voltage source is applied. Okay, so how we are going to see that the motor behaves when the variable frequency current or variable frequency voltage source is applied. That can be discussed by using Norton's equivalent circuit of the synchronous motor. Okay, this is the equivalent circuit, synchronous motor equivalent circuit that we have displaced. And here we see that this E is nothing but your induced EMF. Okay, E is nothing but your induced EMF, and IS is the reference current, and V is the applied voltage. Now, here let us discuss this Phasor diagram. Here, this IF is nothing but this IF is equal to given by E divided by J into XS, and where this will be again written as that is E divided by XS at an angle of minus alpha plus pi by 2. And here you see this IS is the stator current, and E is the induced EMF. Okay, and here this IM, okay, IM is equal to IF plus IS. Okay, this will be displayed with an angle of 90 degree. This will be displayed with an angle of del dash, and this E and this IF will be displayed by an angle of 90 degree. And here you see the mechanical power developed is Pm equal to 3 into E Is cos del pi dash minus pi by 2. If you substitute the value of E, then the mechanical power will be 3 into Xs Is If into del dash. Okay, where T is nothing but your torque, and this torque will be given by this mechanical power divided by omega ms, where K is nothing but your constant, and that is given by 3 into Xs divided by omega ms equal to constant. This K is constant. And here we can notice that the torque, okay, the torque is directly proportional to Is. Okay, the torque is directly proportional to Is. Okay, and one more thing here, for the given value of the Is, maximum torque is obtained. When del dash is equal to pi by 2. Okay, when del dash is equal to pi by 2, we can obtain the maximum torque. Now this Is and induced EMF are in phase, and for that this is the Phasor diagram. In this condition, okay, so under this condition your motor is operating with unity internal power factor. Okay, under this condition your motor will be operated with the unity power factor. Okay, so because your Is is in phase with your induced EMF. Okay, Is is in phase with your induced EMF. Suppose here now how to change, how to make the braking conditions. Here how to achieve the braking conditions. Here from that is from del equal to pi by 2 to minus pi by 2. How to achieve this braking conditions? Means nothing but this del dash is equal to pi by 2 is your motoring operation, and if it is pi by minus pi by 2 means that is a braking operation. How we are going to obtain the braking operation means by reversing the stator current. Okay, by reversing the stator current we can achieve the braking operation. Okay, here it is another here the motor itself has a lagging power factor, and it is desirable to obtain the maximum torque per unit of stator current. Therefore this is preferred operating conditions. So to how to obtain this braking operation means by reversing the stator current. By reversing the stator current, we can get the braking operation, that is minus pi by 2. Del dash we know that is the angle between the rotating magnetic field which is produced by the stator and the rotor. Now, with this which is produced by the stator and the rotor, and the here for this you will get the maximum torque. Okay, so under this condition you will get the maximum torque. Next, we will discuss about the brushless DC motor. So before that, we should know what is meant by brushless DC motor. Here, brushless DC motor consists of rotor in the form of permanent magnet. Okay, brushless DC motor. First, generally, I am going to discuss brushless DC motor is the nothing but it consists of rotor in permanent magnet, and the stator will be in the form of polyphase armature windings. Okay, and the stator will be in the form of polyphase armature windings. So it differs from conventional DC motor. The brushless DC motor differs from conventional DC motor, and such that it does not contain brushes. It does not contain brushes, and the commutation is done by using electrically. Okay, and the commutation is done using electrically. Using electronic drive, we are going to do the commutation. Okay, using electronical drive, we are going to do the commutation. And the brushless DC motor, the stator and the rotor flux, okay, the stator and rotor flux are maintained constant. Okay, and maintain constant angle between between them. Okay, so between the stator and rotor, which is similar to that of your DC motor. Okay, and here the brushless DC motor is actually DC powered. Okay, the brushless DC motor is actually DC powered, but the inverter is connected which converts it to AC. Okay, the inverter is connected which converts it to AC. So here the controller is the here static units which converts the AC motor to DC motor. This is the cross sectional view of your permanent magnet, trapezoidal permanent magnet AC motor. Okay, the cross sectional view of permanent magnet AC motor. This is the current regulator voltage source inverter circuit, and see here, here the thyristors are switched on sequentially. First TR1 will be turned on, and TR2 will be turned on, and TR3 will be turned on, and TR4, TR5, like that it will be sequentially, it will be turned on and off, and the current will be flowing within the limited range. Okay, the current will be flowing within the limited range. It will not go beyond the ranges. Okay, so like that we are going to design the circuit. The transistor will be turned on and off continuously, such that to flow to make the current flow into the circuit within the limited range. Okay, so thank you students.